January 1940. The frost still clung to the edges of a small English farm. Wisps of smoke curled from a crooked chimney, mingling with the cold morning mist. The earth was hard, unyielding, yet one man bent over the soil with quiet determination. John Thompson, a middle-aged farmer with sun-lined skin and calloused hands, sprinkled an unusual mixture over his fields, a combination of chemicals he had been experimenting with for months. To anyone passing, it was merely fertilizer, a strange blend that promised better yields in an unforgiving winter. But this was no ordinary farming experiment. Deep within the barns, sacks of this peculiar mix waited, untouched by the wider world. Outside, the distant hum of war was growing louder. Europe was on the brink, armies were mobilizing, and governments were desperate for resources, for innovations, for advantages no one had yet imagined. In the quiet of his fields, Thompson's simple discovery was about to leave the furrows of his land and travel into the skies above Europe, carried within the bombs that would redefine modern warfare. By 1939, the world had already learned the bitter lessons of the First World War. Europe teetered on the edge of another cataclysm. Germany, under Adolf Hitler, had begun its rapid expansion, invading Poland in September, sparking a chain reaction that pulled France, Britain, and later the Soviet Union into the conflict. The skies buzzed with reconnaissance planes, the seas bristled with warships, and the ground shivered under the march of mechanized armies. In the midst of this escalating chaos, Allied planners faced a critical problem: munitions. Bombs were not just weapons. They were instruments of strategy, morale, and national survival. Yet the ingredients for their production, particularly nitrates and other explosive compounds, were in short supply. Traditional sources, such as Chilean saltpeter, were difficult to import due to naval blockades and the constant threat of German U-boats. Factories strained under demand, and military engineers raced against time to secure alternatives that could sustain a war of unprecedented scale. In laboratories and industrial plants across Britain and the United States, chemists experimented tirelessly. Every potential source of nitrogen, every chemical compound that could be safely transformed into high-explosive material, was scrutinized. Among the overlooked and mundane sources of nitrogen were fertilizers, widely used in agriculture. Ammonium nitrate, a compound long celebrated for enhancing crop yields, emerged as a candidate for military application. Meanwhile, back on the countryside, ordinary farmers carried on with their daily work. To the world, a farmer's field was nothing more than soil and seed, sunlight and rain. But hidden within the routine of sowing and tending, certain individuals stumbled upon chemical formulas that caught the attention of military scientists. Their discoveries were modest in appearance, just blends of nitrate compounds, seemingly innocuous, yet they possessed the potential to be transformed into powerful explosives. The race for innovation was urgent. Intelligence reports warned that Germany's Luftwaffe and mechanized divisions were growing stronger each month. Allied command recognized that technological advantage would determine not only victory, but survival. Precision bombing, targeting factories, transportation hubs, and strategic positions required bombs that could be produced in large quantities with consistent reliability. Ordinary production methods could not meet these demands. Alternative sources of explosives were needed, and fast. In this environment, a curious intersection of agriculture and warfare began to emerge. Fertilizer, a substance associated with life and growth, suddenly carried the potential for destruction. Military scientists began to study the chemical properties of ammonium nitrate, analyzing its explosive potential, stability under storage, and adaptability for mass production. Every small discovery, every incremental improvement, could tip the balance in the Allies' favor. Farmers, unwittingly, became unlikely contributors to the war effort. Their experiments with crops, soil nutrients, and fertilizer blends were not yet known to the broader world, but their work would soon travel from rural barns to munitions factories. It was a transformation that would turn humble fields into the foundation of a new kind of weapon, a weapon capable of shaping the outcome of battles and, ultimately, the course of history. In this moment, the line between civilian life and military necessity blurred. The war was no longer confined to soldiers in trenches or pilots in the sky. Innovation was everywhere, in the labs, in the factories, and even in the hands of farmers tending to their winter crops. And it was within this quiet, frozen, January landscape that John Thompson's strange fertilizer mix would catch the attention of those who could see its lethal potential. The world was preparing for conflict on a scale never before witnessed. Yet in the midst of global mobilization, a simple chemical blend, born of soil and sweat, was about to change the battlefield in ways few could predict. By early 1940, Allied engineers and chemists had begun translating theoretical discoveries into practical applications. Ammonium nitrate, the same compound that farmers like John Thompson had been experimenting with to enrich soil, revealed a remarkable versatility. When combined with other stabilizers and oxidizers, it could produce a high-yield explosive that rivaled traditional munitions derived from imported nitrates. The implications were immediate. The Allies could now reduce dependence on foreign sources, accelerate production, and equip air forces and artillery units with bombs that were both powerful and consistent. Laboratories in Britain, Canada, and the United States worked feverishly. In industrial halls, technicians ground, mixed, and tested compound after compound, documenting each variation with meticulous precision. The challenge was not merely chemical, it was logistical. Fertilizer-derived explosives had to be safe to store and transport, stable under varying temperatures, and adaptable to the shapes and sizes required for different types of bombs. One miscalculation could result in catastrophic factory accidents, as industrial chemists knew all too well from decades of precedent. Meanwhile, farmers like Thompson remained largely unaware of the broader significance of their work. Their fertilizers, intended to coax crops from reluctant soil, contained the very elements that military engineers now recognized as vital for the war effort. Reports filtered from local agricultural boards to chemical consultants in London. High nitrate yields observed in experimental plots. These seemingly mundane observations, when interpreted through the lens of wartime necessity, became the first threads connecting rural fields to the arsenal of modern warfare. The British Ministry of Supply began formal programs to identify and acquire large-scale sources of ammonium nitrate. Factories were repurposed, fields were surveyed, and agricultural industries were consulted. In North America, the U.S. War Department initiated similar investigations, realizing that domestic fertilizer could serve as both a supplement and a substitute for imported explosive ingredients. By mid-1940, the collaboration between farmers, chemists, and military planners had evolved into a systematic effort to harness these unconventional resources. At the same time, the global conflict was escalating. The Luftwaffe dominated the skies over Europe, while German panzer divisions rolled through the Low Countries with astonishing speed. Britain faced the looming threat of invasion, and Allied planners understood that precision bombing campaigns could buy critical time and disrupt German supply lines. The bombs themselves, therefore, were not just tools. They were strategic instruments whose effectiveness depended on chemical reliability as much as design or delivery. The stakes could not have been higher. In this context, John Thompson's fertilizer mix was not unique in its chemical composition, but it became symbolic of a broader pattern. Ordinary life intersecting with extraordinary necessity. A farmer's experiments, combined with scientific ingenuity, offered a solution that bureaucracies and battle-hardened generals could deploy on the front lines. The seemingly accidental convergence of agriculture and warfare illustrated a recurring theme of the conflict. Innovation often arose in the most unexpected places, and the outcomes depended as much on human insight as on raw materials. By the close of 1940, the stage was set. Fertilizer-derived explosives were no longer theoretical. They were being manufactured, packaged, and shipped to airfields and artillery depots across the Allied world. The next step was transformation, turning the knowledge of farmers and chemists into weapons capable of altering the trajectory of battles. In the hands of pilots, bombardiers, and engineers, these humble compounds would become instruments of destruction with a precision and scale never seen before. The quiet frost of January fields, where Thompson had sprinkled his curious mix, now connected directly to the thunderous campaigns in Europe. From soil to bomb, from barn to battlefield, the lines between civilian industry and military innovation had blurred completely. The next phase of this story would examine the multiple angles through which this transformation unfolded: human ingenuity, technological adaptation, tactical advantage, and the leadership decisions that brought these bombs to war. John Thompson, like countless farmers of his generation, was defined by rhythm. The seasons dictated his work, and the soil demanded patience. Yet, in the quiet of early mornings, amidst frost and fog, Thompson's curiosity set him apart. His experiments with nitrate-rich fertilizer were never intended for war. They were born of practicality and a desire to improve crop yields. He kept meticulous notes, adjusting ratios of ammonium nitrate and other minerals, observing how seeds sprouted, how plants thrived. Little did he know that the same compounds nourishing his fields would soon fuel a global conflict. His story was emblematic of an unexpected truth in WWII. Ordinary individuals, far removed from battlefields and command rooms, were capable of altering the course of history through ingenuity and persistence. The human element, the farmer's intuition, patience, and careful observation was as crucial as the laboratories and factories that would later convert his discoveries into explosives. From the laboratory perspective, Thompson's fertilizer mix offered a technological breakthrough. Chemists dissected its components, identifying the optimal combinations for explosive yield, stability, and transport safety. Ammonium nitrate, previously relegated to agricultural use, became the backbone of munitions production. Engineers worked to adapt these compounds for bombs, shells, and artillery charges, balancing the delicate need for power with the imperative of safety. Small variations in chemical proportions could spell disaster or success. Factories installed controlled environments, precise mixing equipment, and rigorous testing protocols to ensure that every batch performed predictably. The transformation from soil amendment to high-explosive material represented a fusion of agricultural science and military technology, illustrating the adaptability required in total war. The availability of fertilizer-derived explosives shifted tactical calculations for Allied commanders. Previously, production limitations had constrained bombing campaigns, restricting the frequency and scale of missions. With a domestic source of reliable explosive material, air forces could plan sustained operations against strategic targets, railways, factories, and fuel depots critical to the Axis war machine. Pilots and bombardiers could rely on uniform detonation, increasing accuracy and lethality. Artillery units similarly benefited, with shells standardized for predictable range and impact. On the ground, engineers and infantry observed the effects: obstacles destroyed, fortifications breached, enemy supply lines disrupted. The tactical advantage was subtle but profound: an invisible current flowing from the quiet farm fields into the heart of operational planning. Military leaders quickly recognized the strategic value of these unconventional explosives. British and American generals, confronted with the logistical challenges of sustaining a prolonged war, saw in ammonium nitrate a solution to both scarcity and scale. Memoranda from the Ministry of Supply emphasized the reliability and adaptability of fertilizer-derived bombs. Commanders in the Royal Air Force and U.S. Army Air Forces began incorporating these munitions into operational planning, adjusting sortie numbers, target priorities, and timing to exploit this newfound resource. The decisions were not made lightly. Leaders weighed the advantages against potential production risks, transport hazards, and the ethical implications of introducing a civilian-origin compound into the machinery of destruction. Their foresight ensured that an innovation born in farmland could be deployed with precision on the battlefield. Meanwhile, German intelligence was struggling to understand the sudden increase in Allied bombing efficiency. Reconnaissance reports indicated larger payloads, more frequent raids, and a consistency in detonation that suggested a breakthrough in explosive technology. The Axis powers, dependent on imported materials and increasingly strained by blockades, found themselves at a disadvantage. Engineers in German munitions factories attempted to replicate or counter the Allies' explosive capabilities, but supply constraints and secrecy surrounding fertilizer-derived production limited their options. What the Germans could not see was the unassuming origin of the innovation. A farmer's experimentation in a frost-covered field thousands of miles from the front lines. The human and logistical narratives intersected invisibly, with rural ingenuity quietly undermining enemy calculations. The moral dimension of this innovation was complex. Fertilizer, a substance associated with growth and sustenance, had been transformed into an agent of destruction. Soldiers and civilians alike would witness its effects in the form of bombs raining over cities, factories, and fortifications. Chemists and military planners faced a paradox. They were harnessing life-giving compounds to kill. Yet, in the calculus of total war, this was a necessity. The ethical tension highlighted a broader truth about WWII. Survival often depended on repurposing resources in ways unimaginable during peacetime. Ordinary acts, fertilizing fields, experimenting with soil, could ripple outward, affecting thousands of lives and altering the trajectory of entire campaigns. Through human ingenuity, technological adaptation, and strategic foresight, a simple farmer's discovery had rippled across continents. Fertilizer, once confined to pastoral fields, now underpinned the bombs that would define air campaigns over Europe. The convergence of innovation, leadership, and necessity set the stage for a decisive moment. A turning point in which the quiet work of a single individual would resonate across battlefields, changing the course of engagements and, ultimately, history. Spring 1941. The skies above Europe were thick with the hum of engines and the whine of anti-aircraft fire. The Royal Air Force, equipped with newly produced bombs derived from ammonium nitrate, prepared for one of the first large-scale raids against German industrial infrastructure. Factories in the Ruhr Valley, a hub of steel production and armament assembly, lay in their crosshairs. Pilots checked instruments, synchronized watches, and mentally traced the flight paths that would carry their deadly cargo over enemy territory. On the ground, Thompson's fertilizer mix had been transformed in factories across Britain and the United States. Engineers had optimized the chemical ratios to maximize explosive yield while minimizing handling risks. Bombs were meticulously inspected, packed into squadrons of Lancaster and B-17 bombers, and loaded under the watchful eyes of technicians who knew that one misstep could spell disaster. Each bomb carried within it a connection to ordinary fields, to soil, and to a man who had never imagined that his small experiments could influence the fate of nations. The raid commenced at dawn. Bomb bays opened over target zones, and the sky erupted in flashes and plumes of smoke. For the first time, Allied planners witnessed the tactical power of fertilizer-derived explosives on a massive scale. Bridges were severed, assembly lines halted, and ammunition depots obliterated. Ground reports confirmed the effectiveness: consistent detonation, predictable blast patterns, and remarkable destructive potential, all from compounds once intended to nourish crops. German engineers and factory supervisors scrambled to assess the damage. Air raid alarms rang across the Ruhr, and emergency crews worked frantically to salvage machinery and infrastructure. Intelligence reports began to note a worrying trend. Allied bombs were hitting with unprecedented accuracy and volume. Analysts speculated that a breakthrough in explosives production was behind the sudden increase in efficiency, but the origin, an unassuming farmer in rural England, remained unknown. The success of the initial raids emboldened Allied command. Squadrons were tasked with increasingly ambitious missions. Industrial centers, fuel depots, and transport hubs became targets. Each sortie relied on the reliability of the fertilizer-derived bombs, enabling planners to coordinate attacks with strategic precision. Pilots who had flown countless missions noted a difference. The bombs behaved predictably, the detonations were uniform, and the resulting damage allowed for repeatable tactical calculations. The edge gained through chemical innovation translated directly into operational advantage. Yet the turning point was not only technological, it was psychological. Soldiers and commanders recognized that a new era of warfare had begun, one in which ordinary resources could become decisive instruments of battle. Morale among Allied pilots soared, bolstered by confidence in their equipment. On the opposing side, German forces faced an unsettling reality. Even as defenses hardened, the Allies possessed a capability that could strike reliably, repeatedly, and with devastating effect. This moment marked a shift in the dynamic of aerial warfare. The integration of fertilizer-derived explosives into the Allied arsenal demonstrated the profound impact of innovation that bridged civilian life and military necessity. The quiet diligence of farmers, the meticulous work of chemists, and the strategic acumen of military leaders converged to create a decisive tool. It was a turning point that highlighted how ingenuity and resourcefulness could overcome material shortages, logistical constraints, and the chaos of global conflict. As the smoke cleared over the Ruhr, the significance became clear. What began as a simple agricultural experiment had transformed into a weapon capable of reshaping industrial landscapes and altering the course of campaigns. The next chapter would examine the continued operations, the enemy's attempts to adapt, and the moments in which this innovation truly shifted the momentum of the war. By late 1941, Allied forces had fully integrated fertilizer-derived explosives into their munitions supply. Precision bombing campaigns intensified, targeting not only industrial hubs, but also transportation networks, ammunition depots, and strategic fuel reserves. The Allies' growing capacity to sustain prolonged aerial operations created operational dilemmas for the Axis powers. German supply lines, once considered secure, now faced systematic disruption. Rail yards were gutted, bridges were demolished, and fuel storage facilities erupted in controlled but devastating detonations. The ripple effect was immediate. Production delays slowed tank deliveries, aircraft assembly lagged, and frontline divisions found themselves under increasing logistical strain. In one notable operation over Hamburg, a fleet of Lancaster bombers dropped hundreds of fertilizer-derived bombs in a coordinated wave. Each explosion followed a predictable pattern, calculated to maximize structural collapse while minimizing wasted ordnance. Observers on the ground reported the systematic destruction of factories critical to aircraft and munitions production. The bomb's reliability allowed Allied commanders to plan with unprecedented confidence. In after-action reports, squadron leaders noted the consistency in yield and blast radius, emphasizing how fertilizer-derived explosives had become a strategic asset rather than a supplemental measure. Axis engineers, meanwhile, scrambled to adapt. German chemists attempted to develop countermeasures or replicate the Allies' process, but material shortages and secrecy within Allied supply chains rendered these efforts largely ineffective. Intelligence intercepted communications described growing confusion and frustration among German planners. Allied munitions now strike with certainty unknown in previous campaigns. The invisible hand of innovation, from rural fields to laboratory benches, was reshaping the operational landscape. The turning point crystallized during coordinated raids on the Ruhr's industrial corridor. Allied forces, equipped with bombs derived from agricultural compounds, executed simultaneous attacks on steel plants, chemical factories, and ammunition depots. The destruction was precise and severe. Military analysts later estimated that these raids slowed German war production by months, a delay that allowed Allied forces to strengthen defensive positions and prepare for larger offensives. In effect, the humble fertilizer mix had become a force multiplier, amplifying the impact of every sortie and mission. Beyond the material effects, the psychological impact on both sides was profound. Allied crews, aware of the reliability and effectiveness of their bombs, approached missions with increased morale and confidence. Conversely, German officers faced the unsettling reality that conventional fortifications and defensive calculations could no longer guarantee security. The unpredictable human element, pilots, bombardiers, and planners, was now paired with a predictable technological advantage. It was a synergy that redefined the nature of aerial warfare. The climactic moment of this transformation was not a single strike, but a series of operations demonstrating the full potential of fertilizer-derived explosives. From the Ruhr to Hamburg, from rail hubs to fuel depots, these munitions proved that innovation born in unexpected places could determine strategic outcomes. Ordinary agricultural materials, when harnessed through scientific insight and military coordination, had become instruments of decisive influence on the battlefield. By the close of 1941, the significance was undeniable. A discovery made in frost-covered fields by an unassuming farmer had cascaded through laboratories, factories, and command rooms to alter the trajectory of the war. Allied planners now wielded an advantage that was both practical and profound: the ability to sustain precision bombing campaigns against the Axis, reduce dependency on scarce imports, and exploit an innovation invisible to the enemy. The turning point was complete, setting the stage for the aftermath, quantifying destruction, assessing strategic shifts, and considering the human costs of this unconventional weapon. By early 1942, the impact of fertilizer-derived explosives on the Allied war effort was undeniable. Industrial centers in Germany and occupied Europe bore the marks of sustained bombing campaigns. Steel plants lay in ruins, railways were severed, and fuel depots had become charred wastelands. Reports from reconnaissance flights confirmed that key infrastructure had been disrupted, delaying production of tanks, aircraft, and ammunition by months. These delays rippled across the front lines, slowing the tempo of German offensives and giving Allied forces critical breathing space to regroup, reinforce, and plan counteroffensives. The quantitative results were staggering. In the Ruhr Valley alone, thousands of tons of bombs, now reliably produced from domestic fertilizer sources, had been dropped by the end of 1941. Factories recorded significant production stoppages, while transportation hubs faced repeated disruptions. Allied engineers noted that the consistent performance of ammonium nitrate-based bombs allowed for accurate planning. Bomb loads could be calculated with precision, sorties timed to optimize impact, and secondary effects such as fires or structural collapse anticipated. In essence, the fertilizer-derived explosives transformed strategy into a predictable science, where careful preparation and execution could reliably achieve objectives once constrained by material shortages. Human stories intertwined with these statistics. Air crews, who had flown countless missions under the constant threat of anti-aircraft fire and enemy fighters, reported renewed confidence in their equipment. Pilots observed that bombs behaved consistently, a difference that saved lives and increased operational effectiveness. On the German side, civilian populations endured the consequences of more precise, heavier, and frequent raids. While Allied planners sought to minimize civilian casualties, the destructive power of these bombs inevitably brought the human cost of innovation into stark relief. The war economy also adapted. Factories previously devoted to conventional chemical production shifted to processing fertilizer-based compounds for munitions. Agricultural boards coordinated with military supply chains, ensuring that nitrate-rich crops and fertilizers could be diverted safely for industrial use. John Thompson and other farmers, whether aware of it or not, had become integral components in a vast, invisible network connecting fields to front lines. Their contributions, once measured in bushels of crops, were now quantified in tons of explosives that reshaped battlefields. Strategically, the Allies gained a new level of autonomy. Dependency on imports, especially vulnerable shipments of nitrates from overseas, decreased. Production bottlenecks eased, and military planners could schedule operations without constant concern for raw material shortages. This shift allowed for greater flexibility, enabling combined operations such as coordinated bombing raids synchronized with ground offensives. Fertilizer-derived explosives were no longer supplementary. They were central to the execution of Allied campaigns and the broader plan to weaken Axis industrial capability. The first phase of the aftermath concluded with the realization that a small, seemingly inconsequential discovery had amplified into a decisive advantage. The fertilizer mix, born of frost-covered fields and careful observation, had traveled through science, industry, and command to leave an indelible mark on the war. Yet, while the material and operational effects were clear, the human and moral implications of turning a life-giving compound into a weapon of destruction remained to be fully understood. These dimensions would emerge more sharply as the war continued, informing both the immediate consequences and the reflective understanding of innovation in wartime. The events of 1941 and early 1942 set the stage for continued assessment. How far-reaching the disruption had been, the responses mounted by Axis engineers, and the broader influence of this unlikely technological breakthrough. From fields to factories, the transformation of ordinary fertilizer into instruments of war had changed the course of campaigns, altering both the physical and psychological landscape of the conflict. As 1942 progressed, the full ramifications of fertilizer-derived explosives became increasingly apparent. Allied bombing campaigns were no longer isolated events, but sustained operations capable of systematically crippling Axis infrastructure. Railways, factories, and fuel storage facilities remained primary targets, and the consistency of ammonium nitrate-based bombs allowed military planners to execute complex, multi-phase strikes with unprecedented precision. These operations, once hindered by unpredictable ordnance and material scarcity, now proceeded with calculated effectiveness. The resulting delays in German war production had tangible effects. Tank deployments slowed, aircraft deliveries were postponed, and munitions stockpiles dwindled. German engineers and strategists scrambled to respond. Intelligence reports noted both confusion and alarm. Allied bombs exhibited reliability and destructive force far beyond prior expectations. Attempts to develop countermeasures were hampered by resource shortages and the inability to trace the bomb's origin. The Axis powers could not reproduce the supply chain linking domestic fertilizer production to frontline munitions, leaving them at a persistent disadvantage. Even defensive measures, reinforced bunkers, dispersed manufacturing, and camouflage could not fully mitigate the effectiveness of these explosives. In essence, a single innovation had altered the calculus of war. The human element remained central. Allied crews gained confidence, not merely from superior numbers, but from the knowledge that their bombs would perform as intended. Engineers and factory workers took pride in producing reliable munitions under challenging wartime conditions. Civilians, however, bore the consequences of increasingly precise bombing. Entire industrial districts suffered damage, and though civilian casualties were often incidental, the moral weight of transforming a life-sustaining compound into a tool of destruction was undeniable. Reports from military correspondents and observers reflected the paradox of progress. The same chemicals that once enriched soil were now agents of devastation, a stark reminder of how innovation could be both constructive and destructive. Economically, fertilizer-derived explosives reshaped production networks. Agricultural supply chains were partially redirected to meet wartime demands, creating a direct link between farms and munitions factories. Policies were enacted to ensure safety and efficiency, and military liaisons coordinated with industrial managers to maximize output. In the United States, the War Production Board monitored nitrate distribution, optimizing shipments for both agricultural and military needs. In Britain, the Ministry of Supply formalized procurement channels, standardizing production and delivery. The invisible threads connecting rural experimentation to industrial-scale destruction now formed a crucial component of the Allied logistical system. Strategically, the impact of this innovation extended beyond individual missions. Fertilizer-derived explosives allowed the Allies to sustain pressure on German industrial capacity, effectively forcing the Axis to allocate resources to repair and defense rather than offense. The psychological strain on German engineers, commanders, and civilian populations compounded the material damage. Repeated, predictable strikes undermined morale, disrupted planning, and contributed to a growing sense of vulnerability. Allied forces, in contrast, could plan operations with a new level of certainty, confident that production constraints would not undermine their strategic objectives. By the end of 1942, the transformation was complete. What had begun as a simple agricultural experiment had become a cornerstone of wartime production, a tangible advantage that shaped campaigns, preserved Allied operational freedom, and demonstrated the profound interplay between civilian ingenuity and military necessity. From frost-covered fields in rural England to the skies over Europe, the journey of ammonium nitrate from fertilizer to bomb symbolized the unexpected ways in which ordinary human endeavor could influence global events. The successes of fertilizer-derived explosives set the stage for reflection, how innovation emerges from unexpected places, how human creativity can both preserve and destroy, and how the quiet work of one individual, John Thompson, rippled through science, industry, and warfare to leave a lasting imprint on history. This understanding would form the philosophical closure of the story, examining not just the tangible outcomes but the deeper meaning of ordinary life. Intersecting with extraordinary circumstances, the story of John Thompson's fertilizer mix is a reminder that history is often shaped not only by generals and armies but by ordinary individuals whose work intersects unexpectedly with the tides of global events. A substance designed to nurture life, a simple blend of nitrates, became a tool of war, demonstrating the duality of human ingenuity. In the quiet frost of an English field, a farmer sought better crops. Across Europe, that same mixture would ripple through laboratories, factories, and battlefields, leaving a mark on the course of WWII. This convergence of civilian insight and military necessity illustrates the unforeseen paths through which innovation can emerge. Science, once confined to experiments in fields or labs, found application in the machinery of warfare. The predictable behavior of ammonium nitrate-based bombs gave Allied commanders a tactical and strategic advantage. Yet it also highlighted the ethical complexities of transforming life-giving resources into instruments of destruction. War has always demanded adaptation, but rarely is that adaptation so intimately tied to the ordinary, so rooted in the rhythms of everyday life. The narrative also underscores the profound human element behind technological progress. Farmers, chemists, engineers, and pilots each played a role in a chain that stretched from soil to sky. Their collective efforts shaped outcomes that statistics alone cannot capture. The confidence of air crews, the recalibration of enemy strategy, and the psychological weight of innovation on both sides of the conflict. One man's quiet experiment had evolved into a lever capable of shifting battles, campaigns, and the perception of what was possible in total war. In reflecting on this story, we see that history is rarely linear. Small, seemingly inconsequential actions can reverberate across continents, influencing decisions, strategies, and outcomes in ways no one could have anticipated. The frost-covered fields of England, the buzzing of laboratories, and the thunder of bombs over Europe are all connected. And in that connection lies a lesson: human curiosity, when combined with circumstance and necessity, can leave a mark on history as profound as the largest battles, the most decisive strategies, or the most celebrated leaders.